Hello Year 10, Mr. Mumford from his office stroke shed once more on a glorious sunny day in April. Hope you're all well. This video is all about atmospheric pressure. So first of all, I'd like to start you off with a little problem, and I do think you should freeze the video, have a think of it for a minute, and then carry on, and I'll explain how, well, I'll give you the answer right at the end. Anyway, you're going on holiday. Yes, some days when you actually fly again. When you buy a bottle of pop in the airport, you take the half-drunk bottle in the aeroplane because you want to drink it. Obviously, you can't carry it through security. During the flight, you notice your bottle seems to have expanded and now difficult to squeeze. Why? Well, I would have started off at the beginning of the lesson, and this sort of thing they can ask examination questions, and you have to basically use keywords to explain it. So, I'll advise you, freeze the video, put some ideas down on a piece of paper, and we'll see you right at the end or not of the video. Anyway, as you'd probably noticed, this lesson is all about atmospheric pressure. What you've got to be able to do is describe a model to explain atmospheric pressure and also explain why atmospheric pressure decreases with height. So, first of all, to get you back is what causes air pressure or atmospheric pressure. Now, this does go back to the unit you did before, all about particle model, and we did look at pressure then. And some of you may remember this little video simulation. What you've got is a container here. Don't worry about this little man at the moment, we ignore him. But anyway, the container is got nothing inside it, it's a vacuum. And what I've got here is a super duper pressure recorder. Now, it is recording ATM, and ATM is atmospheric pressure, but I'll come back to it in a second. But first of all, I want to show you what pressure, or air pressure, or atmospheric pressure, how it is created. So what I can do here is I've got a special pump, and what I can do is I can basically pump in some air particles. Now these particles, we know, in a gas move around all very, very quickly. And the first thing we notice is the fact the particles collide with the walls and bounce off. Now, because these particles collide with the wall, they create a force. And the work we've done before, we know that pressure is force divided by area. Therefore, if they exert a force on the wall over a certain area, they're going to create pressure. Now you can see here the pressure is going up, and it's going up to about 0.62, 0.6-ish. And it does make sense if I now pump in more air particles. Now I've got more particles hitting the wall, therefore more particles hitting the wall create greater force. Because I've got more force over a certain area, bingo, the pressure goes up. So to go back into this one here is, this is why we get atmospheric pressure. Now here is, I've got a picture of a helium balloon, and you've got helium inside there creating pressure, and I've also got the atmospheric pressure on the outside. So to get down to nitty gritty of this, you've got to be able to use keywords. So what creates this pressure is you've got fast moving, I'll write this down for you, fast moving gas particles. And the particles are moving around very quickly. Okay, what they can do then is they basically collide with walls, or it could be the balloon is the case here. Then that is going to exert a force, and change this over a certain area, and then that's going to go to create air pressure or atmospheric pressure. Okay, important thing to come in here is you're getting your keywords. You're talking about fast moving gas particles. They're going to collide with the walls. That's going to exert a force over an area, and that's going to create the air pressure. Okay, so to show you, this is a cool demonstration which I do in the lab. Obviously I'm going to have to do it through YouTube for the time being, but it's a really, really cool one. And I think it's this one here. Oh, yes, there we go. Yeah. Now, I like this. This is called the upside down trick. I know you're very excited, aren't you? Upside down trick, and you can try it at home. Is basically you get a glass full of water. You put a piece of paper on the top of it, and then you turn it upside down. Look at that! When you take your hand away, the paper stays there. Now, when you do try this at home, I would advise you to do it over a sink, because if you get it slightly wrong, it will go completely pear-shaped and the water goes everywhere. Now, getting rid of that. Why does that work? Well, this is a classic example of, I'm trying to use shapes here. I'm going to be very, very bold and brave, trying to make a shape. Okay, there's going to be my glass, which now has gotten to a cuboid shape, but never mind, that'll do. Okay, here's going to be a glass, and that's full of water. I know it's orange, but there you go, we'll do water. Now, what you've got on the bottom of it is you've got your card, which is going to be all the way along like this. And I've drawn my card in red and one step black, but never mind. Okay, now, with the case here, you know already, water is acting downwards with a weight. So the weight of the water here acts downwards there. But the important thing is, if the water is not going to fall out, there must be an equal and opposite force acting upwards. And that's due to the weight of water. And this is atmospheric pressure, or air pressure. But because it's coming from our atmosphere, I'm going to call it atmospheric pressure even. Okay, now that shows you that atmospheric pressure, it really is very, very big. And it's roughly about 100,000 newtons per meter squared, or 100 kilopascals. Now, it's not constant. It does change a bit because atmospheric pressure changes around the world. Hence, the moment, a nice blue sky day, it's high pressure, and you may have heard about that. You also get low pressure days, but it's roughly around about 100,000, but it will vary. It's about 990, you can go up to 101, 106, depending on the weather. Now we're happy with that. There is a fantastic experiment which I've done at home just for you. I would have done it in the lab with you as well, which I love doing this one. Is you get a can, and I've got a nice smiley can for you. I know you appreciate that. And what you do is, I'm going to use my blue pen now, is you put a little bit of water in the bottom here like this. Okay, then what you do is you heat it using a Bunsen burner in the lab, and you put a lot of heat in, and eventually this water will start to boil. Oh, better get a colour pen that we can see. It will start to boil, and you start seeing steam coming out here. Now, what you do then is you put this straight down into a container of cold water. And what that does then, beforehand around here, you got lots of steam. It condenses that steam because it's very, very cold. And what it does then, it reduces the air pressure inside this can because there's hardly any particles there. It doesn't quite cause a vacuum, it causes a pass-through vacuum. Therefore, if you then got the outside pressure still acting on it, if you then remove all the air inside here, so you've got no pressure pushing out, unbalanced forces, won't the can collapse? Now, to show you happening in action is a video I did in my kitchen. Now, here's the can, and what we're doing here, I've got a little gas stove out, I'm boiling the water in the can, and here's my beaker of cold water, and slowly but surely, I've gone slow mode here, it's all very, very exciting, is I'm going to take this can here, I'm going to take the can, I'm then going to take it vertically down, and yeah, you can hear the cow yawning away there as well, can't you? There you are. Put it in and watch that can go. Bang. And basically, it takes a while for it to happen because you're condensing the air inside, and as soon as you condense it, then the atmospheric pressure is going to be larger outside, and the can crushes. Cool little video. Now, to go along with that then, is you need to know why air pressure decreases with height. Now, in other words here, is if you go higher and higher in the atmosphere, for example, you can go on top of Mount Everest, if you wanted to. On top of Mount Everest, atmospheric pressure is a lot less. Now, this is because when you are down near the center of the Earth about here, can you see lots and lots of air particles? Therefore, the density of this air is going to be high. When you go higher up in the atmosphere, the air is a lot less dense, therefore you've got less particles. Doesn't that make sense? Down at the bottom, you're going to have more collisions. If you're going to have more collisions on the bottom, won't the pressure then has to increase because you've got greater force? On the top, you're going to have less collisions there of all these particles flying around. Therefore, the pressure must go down. Another way of looking at it is looking at weight. If I'm down here, isn't the weight going to be bigger? And we have done the equation before that pressure equals height multiplied by density multiplied by g. You've got a greater weight of column air above you. So then it really explains why pressure decreases with height. And we go higher and higher and higher, pressure is going to be less. Therefore, to go back to my question here right at the beginning, it explains this. Because when you've got your bottle on the bottle and the airplane, and when you're at the airport, is you have got atmospheric pressure pushing in like this. And if you've got it half empty, you've got the pressure pushing out. But as you go higher and higher and higher and higher, what happens then is the atmospheric pressure on the outside, this one, is going to start decreasing. Therefore, quickly sketching my bottle here again, like this, I know it's a very quick sketch, is now this force outside is going to be very, very small. And therefore, this one here inside is going to be bigger because it's the same it was when it's at the surface of the Earth. Therefore, if the outwards pressure is going to be greater than the outside atmospheric pressure, the bottle becomes incredibly hard and it's very difficult to squeeze. Okay, so to summarize what we've just done, we've just been through describing a model, explain atmospheric pressure, and I've also done with you explain why atmospheric pressure decreases with height. Hope you enjoyed the video.